Hello, welcome to the Recitation Week 8. Today I will be discussing the step response of the first and second order systems. So basically, we want to find what is the time domain solution of first and second order systems with respect to input step. So for first order system, we have the following system. R of s is the input, C of s is the output, and the transfer function of the system is A over s plus A. And what is the time domain solution here? So what is C of t given R of s as a step input? To compute that, then we do the following. So C of s is A over s plus A times R of s, right? But since R of s is a step input, then we have this term right here, A over s, so this will be s times s plus A, and then we can use partial fraction expansion to find C and B over here, right? And you can do that very easily, and we get C equals to 1, B equals to minus 1. So we have C of s is 1 over s minus 1 over s plus A, and from here we can directly use the Laplace inverse transform from the Laplace table, and we get C of t is 1 minus e to the power minus at for t greater than or equal to 0. Okay, this is the time domain solution. For first order system, we have three measures. The first one is time constant, which is the time that it takes for the system from 0 to 63% of the steady state value. So the time constant t is 1 over a second. And rise time, what is rise time? Is the time that it takes for the trajectory of the system starting from 10% of the steady state value to 90% of the steady state. And the third one is settling time, so the time that it takes for the system to settle to around plus minus 2% from the steady state value. Okay, so given first order system with the following transfer function, then you should be able to compute the time constant, rise time, and settling time. So this formula you can use it very easily. How about second order system? For second order system, then the convention is that we have this following transfer function, b over s squared plus as plus b, where b is omega n squared and a is 2 zeta omega n, where omega n is the natural frequency of the system. So what is the frequency of the system without damping? So that's the natural frequency of the system, and zeta is the damping ratio. Okay, so the behavior of the second order system will depend on the damping ratio and also the natural frequency of the system itself. Similar to the first order system, we have several measures for the time domain solution of the system given a step input. Okay, so remember that for this time domain analysis, we always assume that the input is step function, and we want to find the trajectory of the output given this step input. Okay, we also have rise time here. So rise time is pi minus beta over omega d. So I need to remind you that rise time is the time that it takes for the system starting from 10% of its steady state value to 90% of its steady state value. Rise time is pi minus beta over omega d. Omega d is defined as omega n times square root of 1 minus zeta squared, whereas beta is the tangent inverse or inverse tangent of omega d over zeta times omega n. Alright, see that from this transfer function b over s squared plus as plus b, then you should be able to compute zeta and omega n, right? Because omega n is the square root of b, take the plus sign because natural frequency is always positive. And once you compute the natural frequency, then from A, which is 2 zeta times omega n, you can compute the damping ratio zeta. All right, so that's the first step. You need to extract omega n and zeta. Afterwards, you can compute the rise time using this formula. And the settling time, which is the time that it takes for the system to settle around plus minus 2% of its steady state, is given by 4 over zeta times omega n. So 4 over, in the parentheses, zeta times omega n. Okay. In contrast to the first order system, then for second order system, we have more complex response. So for example, for underdamped system, then the system will oscillate first before it reaches to its steady state value. For example, for underdamped system, then the system will start from 0, assuming 0 initial condition, and it will rise high above the steady state value, but it will go down and oscillates, and then it will settle to its steady state value. And the percent overshoot, which is, we refer this value right here is overshoot, which is the value as it which is over the steady state value, as percent overshoot. So for example, if the percent overshoot is 50%, then it will rise around 50% more than its steady state value. Okay, and the percent overshoot can be computed using this formula. So e to the power minus zeta pi over square root of 1 minus zeta squared times 100%. Another important measure is peak time. So when it will reach the maximum overshoot, which is the time that it takes from 0 to its maximum overshoot, which is t. P is pi over omega d, which is pi over omega n times square root of 1 minus zeta squared. You see, if we are talking about time, right, like rise time, settling time, peak time, then the unit must be in second. Overshoot is the percentage, and omega n is a frequency also, as well as omega d. Since omega n is in radian per second, then omega d is also in radian per second, because damping ratio doesn't have any unit. Since omega n is in radian per second, so omega d is also in radian per second. Okay, so be careful with the units when you are working with this kind of systems. Make sure that you understand the units. Okay, having discussed the first and second order systems, then let's solve some problems. So here is the first problem. We have a very simple RC circuit, and we have 5-volt supply. It's a DC voltage supply. We have a switch, we have a resistor, capacitor. The resistor is 1.8 ohm, capacitor is 0.79 farad, and we have also a switch. When t is equal to 0, then the switch will be closed. So the question is, what is the trajectory of the voltage across the capacitor, which is the output voltage is the voltage on the capacitor, say this is plus minus, for t greater than equal to 0. Okay, so how do we compute it? So we can use the concept of impedance. So the output voltage in frequency domain or in Laplace domain is, we know that the impedance in Laplace domain of capacitor is 1 over SC. So 1 over SC over R plus 1 over SC times the input voltage Vi of S. We can simplify this further into S1 over SRC plus 1. Since the input is a step function with 5 volts of magnitude, then we just have 5 over S, right? And what is RC here? So RC is 1.8 times 0.79, which is approximately 1.422, right? So we have 5 1 over 1.422 s plus 1 times 1 over s. You can simplify it such that we have this form, so a over s plus a. So we can divide the numerator and denominator with 1.422, which is 1 over 1.422 s plus 1 over 1.422 1 over s. So 1 over 1.422 can be approximated by 0.7 s plus 0.7 times 1 over s. Okay, so from here we know that the solution is phi o of t is 5 1 minus e to the power minus 0.7 t for t greater than or equal to 0, right? Because if you can compare it with this formula, so 1 minus e to the power minus 80. And what is a here? So we know that a is 0.7, right? So from here we can easily compute the time constant tau is 1 over a, which is 1.422 second. So remember that if you remember your network theory class, then for series RC network, and the time constant of that system is RC, right? Because here we have it tau s RC, which is 1.422. Okay, what about rise time? Rise time is 2.2 over a, which is 2.2 over 0.7, which is 3.129 second. And settling time is 4 over a, which is 4 over 0.7 is 5.69 second. So from these three, we should be able to plot the trajectory of the system. So this is time, and this is the voltage, output voltage, and we have 5 volts. Surely we have 5 volts. This is 5. Alright, and say it will, from the time constant, then we know that it will reach 63% of the steady state value, which is 5 volt at 1.422 second. Okay, so say this is 50%, this is 60, around this right here is 63%. Say 63% is 1. So let's label the time first. 1 second. Let's do we have 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, so on. Okay, we have at 1.422 we have 63%, so it should be around here. So, and then from the settling time, which is 2%, is 5.7, around 5.7. so here. Okay, so it should look like this: rise, yes, something like that. Okay, So this is the trajectory of the output voltage with respect to time. So this is the final solution. Right, that's the first problem. Second problem. So problem 2. We have mechanical system transitional. So we have spring connected with the damper. There's a damper and there is a mass with mass M, spring constant K, damping constant D, and we pull this mass to the right with force of F of T, and we label the position of the mass as X of T. Okay, the following are given. So the mass is 5, D is 5, and K is 28. So all the units are in standard international units. So mass will be kilogram, damping is Newton second per meter, and the spring constant K is 28 Newton per meter. Okay, so first let us derive the transfer function. So we need to use the Newton's law of motion, which is, so at any steady state, then the sum of force should be equal to 0 at any steady state. So as I'm pulling the system to the right, then the system will react by giving force with equal and opposite direction, right? So F and the mass giving M times the acceleration, d squared x of t over dt squared, the damping minus d over d xt over dt, and the spring minus k x of t. Okay, assuming zero initial condition, then in Laplace domain we have f of s is ms squared plus ds plus k x of s, right? So the front transfer function is x of s over f of s is simply 1 over ms squared plus ds plus k, and by plugging in this value, then we have 1 over 5 squared plus 5s plus 28. Make it standard. So we want s squared to have 1 as its coefficient. So we divide the numerator and denominator with 5. We have 1 over 5 s squared plus 1 s, so just s, plus 28 over 5. Alright, which is what? So this is still not standard, because remember, for second order system we have this form. So b over s squared plus as plus b. But here b, which is 28 over 5, it's not the same here, right? So this is what we want to have, s squared plus s plus 28 over 5. So we also want the numerator to be also 28 over 5, right? So we have to divide here with 1 over 28. Sorry, it's 28. Alright, so from here we see that this transfer function now is in the same form of this one, right? B over s squared plus as plus b. So we can compute directly. From here we know that omega n squared is 28 over 5. hence omega n is square root of it, which is 2.37 radian per second. And also we know that 2 zeta omega n is 1. So from here we know that zeta is 1 over 2 omega n, or 1 over 2 times 2.37, which is 0.211. So zeta, remember that zeta doesn't have any unit, and zeta represents the damping ratio. So we know that the damping ratio of the system is 0.211, which is between 0 and 1. So what does it mean? It means that the system is under damped. So in under damped system, then the system will oscillate, and it will also have something overshoot. So the trajectory should look like this, right? So we want to find the trajectory of x of t given step input on the force. So eventually we need to compute all of this value here, like rise time, settling time, percent overshoot, and peak time. Alright, so let's do that. What is settling time? Very easy, 4 over zeta omega n. So 4 over 0.211 times omega n is 2.37, right? Which is 8.01 second, or it should be 8 seconds, because from here we know that zeta omega n is 1/2, then sampling time is 4 over 1/2, which is 8 seconds. Alright, the next one is rise time. Okay, let's compute rise time. So for rise time we need to compute omega d, which is omega n times square root of 1 minus zeta squared, which is omega n is 2.37 times square root 1 minus 0.211 squared, right, which is 2.31. yes 2.31 radian per second. And what is beta? Beta is inverse tangent of omega d over zeta omega n, which is tangent inverse of 2.31 over 1/2, right? So it gives 1.3576. From here we can compute the rise time directly. So pi minus beta, which is 1.3578 over omega d 2.31, which is around 0.773 seconds. So that's rise time. We also have settling time. The next one is peak time. So when will it reach the overshoot, the maximum overshoot? So peak time is pi over omega d. So pi over 2.31. So the peak time is 1.36 seconds. The last one is the percent overshoot. Percent overshoot is e to the power minus zeta. Zeta is 0.211 times pi over square root 1 minus 0.211 pi. So square root 1 minus 0.211 squared times 100%, it's around 50.7%. All right, so from here we should be able to sketch the trajectory of the output. FT, this 1 2 3 4 5 6 so on, and then let us assume that, so this is x of t, right? Say this is the steady state value. So what is the steady state value here? The steady state value here is 1 over 28. So this 1 over 28, and the rise time is 0.77, peak time is 1.36. so at 1.36 second, then it will reach the maximum overshoot, which is around 50%. so let's say it's around here. It's pretty quick. The settling time is 8 seconds, so it will settle into plus minus of 2% at t equals to 8 seconds. Alright, so let's sketch it starting from 0. Then we know that the rise time is pretty fast, like 0.7723, so it will rise very quickly and then will oscillate with the same frequency. Right, okay, so this is the sketch. It will rise to the maximum overshoot, which is 50.7%. so this is 50.7% of 1 over 28. It will settle at around 8 seconds. It will reach the peak of the overshoot at 1.36 seconds. Alright, so that's the solution. Last problem. Okay, problem number 3. We have the following system. It is a feedback system. We have this block H of S, G of S, output Y of S, U of S as the input. This is negative feedback, plus minus, and don't forget the error, which is over here. It is given that G of S is minus K over S plus 10, H of S is 1. Then the question is find the transfer function Y of S over U of S. B, what is the range of K? So K, this is K over here, such that the closed loop system is stable. C, given K equals to 5, then find the time constant. And D, what is the compute the steady state error. Right, so let's solve. The first one is transfer function, so it should be really easy for you, right? So Y of S over U of S is G of S over 1 plus G of S times H of S, which is minus K over S plus 10 over 1 minus k over s plus 10 plus minus, simplify it, you have minus k over s plus 10 minus k, which is minus k over s minus k minus 10, right? This is the answer for point A. What is the range of k that makes the closed loop system to be stable? We know that the system is stable when the pole is at the uh, open left half plane of the complex plane, right? So we know the real part of the pole to be negative. So we want, what is the pole here? The pole here is k minus 10. We need k minus 10 to be negative, right, for stability. So it means that k should be less than 10, right? So when k is less than 10, then the system is stable. C, given k equal to 5, what is the time constant? Okay, so what is the transfer function here? With k equal to 5, we have minus 5, because k is 5, s minus 5 minus 10, which is minus 5 over s plus 5, right? And then this is nothing but minus 1 times 5 over s plus 5. So this is the transfer function, and if we compare it to the first order system that we have, which is a over s plus a, then we know the time constant is just simply 1 over a. So tau is 1 over a, hence tau, or the time constant, is 1 over a, which is 1 over 5, which is 0.2 second. Okay. D, last one, what is the steady state error? So what is steady state error? So it's limit t to infinity of e of t, right? So since we know that the system is stable, how? Because k is 5, and then we know that the system is stable when k is less than 10. So since 5 is less than 10, then we know that the closed loop system is stable. So we can apply the final value theorem. So limit e of t as t goes to infinity is equal to limit of s approaching 0 for s times e of s, right? So we need to compute e of s. So we know that e of s is, the error is what? U of s minus y of s, right? Okay, so let us divide this with u of s, this with u of s, then 1 minus y of s over u of s. This is transfer function, which is 1 minus 5 over s plus 5, right? So we know that this is, sorry, this is minus 5, so this is s plus 5 minus minus 5, so s plus 10 over s plus 5. So e of s is s plus 10 over s plus 5 times u of s. But we know that the input is step input, so s plus 10 over s plus 5, u of s is 1 over s. Then the steady state error is SSE is limit s approaching 0, s times e of s, which is s times s plus 10 over s plus 5 times 1 over s. They cancel, so limit s to 0 is s plus 10 over s plus 5. By setting s equals 0, then we know that this is equal to 2. So the steady state error of this system with step input is equal to 2. Alright. Okay, so we have reached the end of this lecture, and I hope you can learn from this. And as usual, if you have any question, then do not hesitate to send me email or send Dr. Chow email and come to our office hours. Alright, so I'll see you next week. Goodbye.